Okay. So I feel like the ones that we did at the end of Friday were maybe jumping a little bit too deep. So we'll just make sure that we spend today honing our integration techniques, and then I'm going to show you this lesson one of the two applications that I referred to on Friday. First thing I'm going to do is to rewrite this and rewrite that. So I've rewritten them in index notation before doing any integrating, and I preemptively put in there plus c because I'm so bad at remembering it. So increase the power, divide by the new power. So I'm going to write it like that. Just be clear that that, where I've written it as a single fraction, is exactly the same as that. And you will see both interchangeably. And increase the power by 1, divide by the new power. But of course, 2/4 I can simplify. So I'm going to, having written that, simplify that to a half. So that's 2/4, 1/4. I'm going to get into the habit of doing that sort of simplifying. Here, the half passes through unchanged, increase the power by 1, and divide by the new power. And we talked about this on Friday. I'm effectively a half of something. I'm effectively already saying that's a half. I'm now going to divide by 2 again, so that becomes x to the power of 2/4, or 1/4 of x to the power of 2. So I'll just say that again, because there were a couple of things going on there. A half passes through unchanged. Any coefficient passes through unchanged. X becomes x squared, because that at the moment is x to the power of 1. And then I want to divide by 2. I'm already dividing by 2. That's what finding a half is. So I'm now dividing by 4. So whether you write it like that, or whether you write it like that, it's the same thing. And similarly, with this second one, if I increase half by 1, I get 1/2. Much easier to write that as a fraction. And then I'm going to divide by 1/2. And this is going to crop up a lot. So let's make sure we can remember this now. Dividing by 3/4 is the same as multiplying by 2/3. And I go back to my dear retired colleague, Mrs. Humphrey, who would always say, the 2 pops to the top. So what you're left with is 2x to the power of 3/2/3. So dividing by 3/2 is the same as multiplying by 2/3. And then over here, increase the power by 1, divide by the new power. Dividing by -1, please. You're immortalised on video, how many telling you to be quiet? Where divided by -1 makes it negative, and x to the -1 is 1/x. So what you get there is -1/x, and then 4x power of 4 divided by 4. That's going to simplify down to be just x to the power of 4. So whenever you've used that rule, increase the power, divide by the new power, there's nearly always a little bit of jiggery-pokery that can go on to get the final answer. Now, I've said there are two applications of integration. One of them is undoing differentiating, but there is a second. And so we're not always talking about going from dy by dx to y. So because of that, there is a notation that we use. The notation that we use for integrating is quite an odd one. You put a big swoopy S sign like that in front of the expression. So I'm going to change my dy by dx into a big swoopy S sign. And this then just becomes the answer. There's one other thing you'll always see in an integration question, and it can be ignored. You always have a little dx. And what that means is, it's short for with respect 2x. What that's telling us is that x is the variable. Only need to do the increase by 1, increase the power by 1 divided by the new power for x. So if I've got other letters in there, a, pi, anything else like that, that's not a variable, so I don't need to do any of my increase the power divided by the new power. So the first new thing for today is this notation that we use for integration. This swoopy sign, and I'll show you one from the textbook, and the addition of the dx there, that's not something that doesn't become dx squared over 2. We just ignore it. It's just an indication that in this expression, if there are more than one sorts of letter, it's x that's the variable. It's x that's the variable. So we're going to do We're going to do a few of these ones with the swoopy sign. And these are all frustrating because you end up with an expression that's got this plus c in. And because of that, this sort of integration is referred to in a rather pompous way as indefinite integration. So we're going to be working with indefinite integrals. And an indefinite integral is an answer with a plus c. So we're just going to lever up the difficulty a little bit. Rewrite this as 2x to the minus 3. Rewrite that as 3x to the half. See if you can integrate that. Just like differentiating, when we integrate, we multiply out any brackets first. So multiply out those brackets and then see if you can integrate that. And yeah, that third one, I'll leave you to have a think about. There's quite a bit of sorting out to do with the third one before we get to the increase by 1 power by 1 divided by the new power. So have a go at those 3 examples. They're all going to be indefinite integrals. They're all going to have a plus c in the answer. Right, so for the first one, the integral sign gives us a good way of showing when we are just rearranging and then when we've actually integrated. So going from here to here, I haven't integrated. The sign is still there. So I haven't integrated, I haven't integrated, I have integrated. The sign has disappeared. So I rewrote it as x to the minus 3 and minus 3x to the half. So the first term, when you increase minus 3 by 1, it becomes minus 2. So it becomes 2x to the minus 2 divided by 2, but that's 2 divided by 2, which is 1. So you end up with 1x to the minus 2, which you could have chosen to write as 1 over x squared. And then here you get 3x to the 3 over 2 divided by 3 over 2, so that 2 pops to the top, so you end up with 6 over 3, which is 2. So you end up with 2x to the 3 over 2. I didn't rewrite that, but if you did, that would be 2 times the square root of x cubed. And then I remembered my plus c. It's a miracle. With the second one, I multiplied out the brackets. So x times x squared gives me x cubed, which just becomes that. And 2 over x multiplied by x just gives me 2. And when you integrate 2, just remember it's the opposite of differentiating. So you just get 2x. And I'm not sure we did one of those on Friday, so just make sure that you're happy with that. When you integrate a constant term, you just get that constant term times whatever the variable is, which is x in this case. Plus c. Now with the third one, quite a lot going on here. So firstly, before I do any integrating, 2x squared, that's 2x times 2x, Haven't integrated it, I've just multiplied that bracket out. 2x times 2x is 4x squared. I've then got two things divided by one thing, and one of the first things we talked about was the fact that you can actually write that as two separate sums. Two things divided by one thing. Now, I haven't finished with my rearranging yet, so I'm going to have to do another, oh, and don't forget the dx. I'm going to have to do another integral sign, so that's 4x squared. Now here, I've got, yes, sorry, sure, what am I wrong?
In part A, I'm going to divide by -2.
You're correct, -2, thank you. Should be a -1. Thank you very much, Sean, sorry. I'm in biscuit debt. X to the half divided by x squared. So that's what that sum is. I get a half take away 2, x to the power of -3/2. I haven't integrated yet, remember. I'm still at the rearranging stage. And 5 over x squared, that's 5x to the -2. So there's a lot going on here, and I still haven't integrated. Right, let's integrate. So 4x squared becomes 4x cubed over 3. Increase the power, divide by the new power, 4 passes through unchanged. Increase the power by 1, so -1.5, if you increase it by 1, becomes -0.5, and then I divide by -0.5. I'm going to come back to that one in a minute. And then increase the power by 1, so -2 becomes -1, and divide by -1, don't forget the plus c. There's a lot of rearranging still to do, and I've run out of space. So I'm going to leave that one as it is. This term here, x to the -0.5 is 1 over the square root of x. But the 2 pops to the top. And it's a minus, so it's going to become negative. So what that term becomes is -2 over the square root of x. And then this term here, remember the 5 isn't part of the minus power, so the 5 isn't going to go down below the denominator, that will, and I'm dividing by -1, so it just becomes minus 5 over x. So there's a lot going on there, and we'll get used to it. We'll get used to it. I mean, a lot of these skills seemed a bit odd to start with, but you got used to it. Of course, that's not working, is it? Sorry. So, in the books I've given out, we're on page 291. 291. And this is one of those exercises that gets more difficult as you go through. So page 291, page 292, it's exercise 13b. And I'm just going to encourage you to spend, how long have we got? 15 minutes working at your own pace. Maybe question 1 and question 2 will be as far as you get. Maybe you'll jump over the page and try some of the harder ones. But just practicing this basic nuts and bolts integration. Exercise 13b for those at home. And yeah, have a go. So just for those at home, I've added that exercise to independent study on OneNote just to encourage you to keep practicing that. Okay, so this plus c is frustrating. All right, this plus c is frustrating. I don't like having an answer that has missing values still in it. So how can we deal with it? Well, let me go back to where we started, which was to use integration to undo differentiating, and let me show you how we can get rid of the plus c in those scenarios. So this question here, we're using the alternative notation rather than y and dy by dx. They're using f of x and f dash of x. So we're given f dash of x, which is, and we're asked to find the original function. And that process is integrating. We're not using the notation, but that process is integrating. It also throws in a point that lies on the curve. So let's prepare this for integrating. So I've got two things over one thing. So I can split it up. I'm then going to remember that the square root of x is x to the half. So let's see if we can sort this out. So go for it, Laura. If I do x squared divided by x to the half, subtract the indices, what am I left with?
X to the 3 over 2.
X power 3 over 2, thank you very much, brilliant, yeah. And Harrison, how else can I write 2 over x to the power of a half?
Good question.
How can I write, 1 overs, this is 1 over x to the half, how can I rewrite that as x to the power of something? So it's minus 2x to the minus a half. And that's really important so that I can now integrate. So I'm now going to integrate. So go on then, Callum. X to the power 3 over 2. Increase the power, divide by the new power. Don't give me the final answer, give me your first step.
X to 5 over 2.
Yep.
And then divide it by 5 over 2.
Divided by 5 over 2. Brilliant, thank you. We'll come back to that in a minute. All right, we'll come back to that in a minute. And then, Harry, what about this one here? If I increase minus a half by 1?
Minus 2x to the power of a half. And then divide by half.
Divided by half. Brilliant, yeah, I'll come back to that in a minute. Okay, so we've done our basic integration. We've increased the power divided by the new power. This is the good bit, really. This is where we get rid of the all the horribleness. So my 2 is going to pop to the top. And my 2 is going to pop to the top. And that's over 1, so I'm not even going to bother writing it. Okay, so we've got an expression for f of x. I know before, Ben, I said I'm going to chicken out. I can't really chicken out with this one, so I'm going to have to remember that this is the square root of x to the power of 5. And the 2 isn't involved in that. And that's the square root of x. And at this point, I'm going to switch to the y equals notation. Remember, they're the same thing. dy by dx and y, f dash of x and y. And that's because I'm now going to use this point. The point 4, 5 lies on that curve. So I can now say, right, I know that in this equation, when x is 4, y is 5. And that's just like we do with straight line graphs. Substituting those values in will allow me to work out the value of c. And therefore I can finish the question. So go on. See if you can substitute those values in. And that's why I wanted to rewrite it as square roots. I mean, we could have used our calculator. We could have used our calculator at that point, but I think it's good if we can do these things a little bit manually. So make x equal to 4, so the square root of x is 2, and make y equal to 5, and you should be able to work out what c is. Remember the square root of x to the power of 5, the 2 isn't involved in that, so work out the square root of x to the power of 5 and then just double it. Should get a fifth. This is 2 to the power of 6, isn't it? 2 to the power of 6 over 5. So I subbed it in, I added 8, I took that away, got my calculator. So I can now write my final answer. Which is that, although I guess I really ought to use the f of x notation, because that's what the question was. No one's going to take marks off you for using y equals rather than f of x equals. And no c. So if we are using integrating to undo differentiating, and we know a point on whatever the function we're dealing with is, that's one way we can get rid of the c. So if we flip forwards to page 294 and 295, see if you can get one done. You can either jump straight to question 1 and have a go at one of those, or if you want something a little bit more involved, you can have a go at question 2 or question 3. Just see in the 5 minutes we've got left, you can get one of those done. And similarly, those at home, if you get one of those done, we can pick this up for the next lesson. So we're on page 294, exercise 13C.